Hello everybody and welcome back to another guided video seminar. Last time we started talking about standing waves. And these are waves that are generated by a wave essentially interfering with its own reflection that was jiggling at just the right frequency where you get a special pattern forming. So we saw this on a string where both ends are fixed, and that essentially forced half wavelength increments to be inside those boundaries. So here's our string. We call these points where the wave is completely fixed, it has no motion at all, they are called nodes. And likewise, this point here where the wave is moving the most up and down, that is our antinode. We also saw this on a tube open at both ends. So for example, this would be a flute. Someone is going to blow into a hole in the top. That's going to excite the air inside, causing it to start vibrating. And if they blow at just the right frequency, then what happens is you get maximum amplitude of air vibration on the end. And essentially these are now antinodes. And again, we have a half wavelength. We go from a peak down to a trough, and so that forces us to have a node in the middle. So it's kind of exactly the same structure. The ends have to match, but we have sort of the opposite pattern. Whereas we had an antinode in the center over here, here we have a node in the center where there's no air motion at all. And you can excite higher versions of this where you have more and more nodes or antinodes throughout the center, but this is our basic pattern or fundamental frequency. This is described, the frequencies that you can get to make a standing wave in a tube of a certain length. Again, Fn corresponds to the number of harmonic that we're looking at, whether we're looking at the fundamental frequency n equals 1 or any of the higher vibrations that you can get. So that's equal to the n, the number you're on. So if we were looking for the third harmonic, n would be 3 times the velocity divided by twice the length of the object. So the string has a length from one side to another. That's going to be our characteristic length there. Our characteristic length for the tube is going to be the size of the tube over there. And again, n can be any integer value that we want. So that's what we've seen already. We now want to look at a different kind of instrument. It's going to be a tube again, but unlike the tube that's open at both ends, in the flute you blow into the top and excite the air. In something like a trumpet or a clarinet, where you have a reed instrument, you're basically sealing off one end of the tube with your mouth. And so here we have a sealed off end of the tube. It's a very artistic sketch of somebody's lips. But this side of the tube is now closed off, and as a result, there is no air movement allowed here. Just like our other tube before, we have maximum air movement allowed here. So this scheme here, we have zero air movement here, we have maximum air movement here. Our rule is that this side has to be a node, whereas this side has to be an antinode. And the simplest way we can achieve that is just sort of to connect the dots. Very poorly. That one's a lot better. So in our previous schemes, we had half of a wavelength as our basic increment here. Here, we only have a quarter or a fourth of a wavelength. So this is our one end open pipe. This simulates our brass instruments and our reed instruments. So this is a tuba, a trombone, a trumpet, a clarinet, or a saxophone. All of these are based off a basic unit of a quarter wavelength. So our fundamental frequency for a one end open pipe has only a quarter wavelength inside. We can excite higher frequencies, but if we tried to go to n equals 2. Let's try that and see what happens. Our rule is we have to have a node there. So we're going to start at a node, and we're going to draw, 2 of our fundamental units, so 2 quarter wavelengths. So there's my first quarter wavelength, and my second quarter wavelength gets me back to the center. However, this is not allowed because we have a node paired with a node at the other end, and we have to have opposite features at both ends of the pipe. So n equal 2 is not allowed. We can try to go to the next highest frequency, which would be n equals 3. We start at a node. We're going to do 3 quarter wavelengths. We go 1, 2, 3 quarter wavelengths. So this works. I've ended up back in an antinode at maximum amplitude there, and we can draw sort of the counterpart of that in the other direction. So we have one node located 2/3 of the way across the pipe, and then our antinode is achieved as required at the other end. So this one is allowed. We can try it again with n equals 4, but we're going to run into a similar issue. Now that we have 4 quarter wavelengths, we have a full wavelength in the pipe, and that's going to get us back to another, oops, let's pretend our pipe ends there. You saw nothing. So now we have a full wavelength in the pipe, but this is not allowed because we cannot have a node at the other end of the pipe. So the rule ends up being we're only allowed to have odd numbers for n for a one-end open pipe because of the boundary conditions there. Just as the special frequencies for a string or a two-end open pipe depend on the half wavelength. We have a 2 down here. Our equation for a one-end open pipe depends on a quarter wavelength, and we're going to get just a 4 down there. So that is our formula for a one-end open pipe. N is allowed to be only odd values this time around. So if you were asked to find the first 3 possible values for a one-end open pipe, a trumpet or something like that, you would not plug in 1, 2, 3. The first 3 lowest frequencies are in fact 1, 3, and 5 because the even numbered values are not allowed. So this gives us a way to calculate what sort of frequencies can excite a tube of a certain length. If you were to calculate the length required for a trumpet to make a bass note of a trumpet, you'd end up with something that's absurdly long, and that's why a lot of brass instruments are sort of wrapped up in themselves. The large length you get is accomplished by, twisting the trumpet in on itself, making it possible to carry a multiple meter instrument in your bass hands. What the valves actually do on a trumpet is by pressing down the buttons on the valve, you essentially close off or open up certain parts of this tube, which effectively change your length. So you're not getting different N values by pressing the keys on an instrument like this. What you're doing is you're changing the length, and you're opening up different n equals 1 or fundamental frequencies there. So different notes played by using valves to change length of pipe. So that does it for our discussion of standing waves. We're going to continue talking today with a completely, well, not a completely different topic, but a different enough topic. We're going to look at now the Doppler effect. So put in the simplest terms, the Doppler effect is the change in frequency and therefore pitch due to relative motion between the source of the sound and the listener. So in other words, if you were standing on the sidewalk and you heard a sound from something that was not moving, you would hear that sound exactly as it was produced. If you start having things move toward or away from each other, you get a shift in the frequency of that sound. And so what happens is as things move closer, the pitch increases, it gets higher. So you hear a little whoop. And as objects move further away, the pitch gets lower. So you hear a little whew. So the pitch gets lower. We can think about this by, if we have a source of a sound, a little, speaker, it's going to continually produce sound of a certain wavelength. And if it's staying still, then, it's going to emit a sound at one time. It emitted a sound earlier that's traveled farther away. The next sound that was emitted earlier has traveled further than that, and so on. We can draw these concentric, imagine that these are all equidistant. I'm a really good drawer. Essentially, the wavelength here, these are all taken to be equal distances, at least they're assumed to be. If no motion, we have equal distances. Wave is unshifted. However, now we assume that the same speaker, maybe it's attached to a car of some sort, and it's moving forward with a velocity v. So the wave is always going to be centered on the object, but what happens is it's going to emit a wave, and that wave is going to travel some distance far out from the object. Now the speaker has moved forward a little bit in space, and it's emitted another sound that hasn't moved quite as far, but it's still centered on the object. And then the object moves a little bit further, and it makes another wave that hasn't traveled as far, but it's still centered on the object's new location. And then so on and so on. So what happens is as the object moves forward, again, my velocity vector got eclipsed there, we can see that the waves on this side, they get scrunched up, and the waves on the other side get further and further apart. So when the object goes toward another object, the wavelength shrinks, and the wave crests sort of get more frequent with respect to one another. So the frequency goes up. If we go away from another object, the wavelength grows, and sort of the density of these wave fronts gets less and less dense, and therefore the frequency of those wave fronts decreases. Frequency goes down. I like to think about this another way. The picture's drawn a little bit clearer anyway. This is, sort of what you'll see in a textbook. But I like to pretend that, the source and the object are connected by slinkies. A lot of textbooks will have, a police car or an ambulance, like making the siren sound. There's a lot going on right now. We don't need any more sadness in our lives. So it's going to be an ice cream truck. So here's our ice cream truck. And the ice cream truck's going to play its jingle, Turkey in the Straw or whatever. And we have a kid on the sidewalk who wants an ice cream cone. There's a slinky connected between the two objects. And they are in different planes. This is on the road, this is the sidewalk, so the kid is in no danger here. Don't worry, there are 2 dimensions, 3 dimensions even. And this truck is going to come towards the child. And what happens to the slinky is that slinky is now going to get scrunched up as they approach each other. So the Slinky gets all scrunched up. The coils become denser. And this is analogous to the frequency going up. The coils become more frequent as the objects come together. Likewise, now, maybe the driver had a lot on his mind. He didn't see the kid there, and he drives past him. Here's our Slinky again. The velocity is going to continue towards the right, and as the truck gets further and further away, that Slinky is going to get stretched out. So Slinky stretches and the frequency decreases. So we have this sort of intuition now that if objects get further apart, the frequency is going to decrease. If objects get closer together, the frequency is going to increase. We can represent this mathematically. To figure out, to actually calculate how much that shift is going to be, we can use the following equation. And it's going to look scary at first, but I will demystify it for you. Do not worry. So here we have F1. This is the shifted frequency. That's going to be equal to the original frequency produced by the sound source there's big parentheses, you know something's coming. I'm going to write V here. I'm going to divide it by another V. These V's here, they're not going to have any subscript on them. This is going to be the speed of sound in air, or whatever medium that we're working in. Speed of sound. Up top, you have the speed of the observer. This is the thing that's listening to the sound. The O here is for observer. This is the speed of observer. And on the bottom, we have the speed of the source. I always remember it's O on top, S on the bottom because it's alphabetical order. And then between these symbols, we have plus or minus on top and minus plus on the bottom. So there's a lot here. Let's sort of unpack what's happening here. We have an original frequency. This is the frequency you would hear if there was no motion between anything. Just everything was standing still. It's going to be shifted to another frequency based on how the observer and the source are moving with respect to one another. Now, these signs here. In both the numerator and the denominator, there is a top sign and a bottom sign. So plus on top, minus on bottom. Minus on top, plus on bottom. You use the top signs if that object is moving toward. So you use the top signs if the objects are going toward. So for example, if I have the ice cream truck going towards the kid and the kid is running towards the ice cream truck, they are both moving toward each other. So I would use plus on top for the kid and minus on the bottom to represent that the truck is going towards him. We're going to use the bottom sign if that object is going away. So bottom signs if that object is moving away. So we had top and toward. We could say bottom and bye-bye if you'd like. But we're always going to use the bottom signs if that object is moving away. So let's see an example and see how this actually plays out. So here's our crazy looking equation again. Our situation is going to be a truck honks its horn with a frequency of 550 hertz. It is moving towards a person on the sidewalk at 11 meters per second. The person is walking away from the truck at 4 meters per second. What frequency does the person hear? We'll assume that this is a nice, balmy spring day where the outside temperature is about room temperature, and so V sound is equal to 343 meters per second. So we're going to set up this equation. Our original frequency is 550 hertz. We're trying to find the shifted frequency F1 that the person hears. First thing we need to do is identify who is the observer and who is the source. The truck honks its horn. It's the one making the sound, so VS is the truck, and that is moving at 11 meters per second. The observer is the person, the one that's hearing the sound, and they are moving at 4 meters per second. So V here is 343 in both cases because that's the speed of sound regardless of whether you're the truck or the person. The person, they are moving away from the truck. So regardless of what the truck is doing, the person's motion is directed away. So we're going to use the bottom sign up top for the observer to say that the person is moving away, -4. The truck is moving towards the person, so regardless of what the person is doing, the truck is trying to get closer to the person, and we're going to use the top sign for toward. We're going to get a minus on the denominator. And then the truck is moving at 11 meters per second. So we're going to get 550. We're getting 343 minus 4, that's 339. 343 minus 11, that is 332. And when we work out this ratio, we get a value of 562 hertz. So the frequency went up from what it went before, and this makes sense. Even though the person is trying to move away, the truck is getting to him faster than he could ever go, and so therefore the net motion is a together motion. So it makes sense that the frequency increased because truck and person are going to get closer together. So why do we use the top signs for together and the bottom signs for moving away? Think mathematically about this equation. If the objects are coming together, we want to make the frequency as large as possible. So we do that by making the numerator bigger, adding 2 numbers, and making the denominator smaller, subtracting 2 numbers. Likewise, if they are coming away from each other, we want to make the frequency as small as possible. So we want to make the numerator small by subtracting 2 numbers, and we want to make the denominator big by adding the 2 numbers. So we can think about this not only in terms of like Slinky, stretching, or compressing, but we can also think about it in terms mathematically. What is this equation telling us? So like if closer, we want to maximize numerator and minimize denominator. And if far apart, we want to minimize the numerator and maximize the denominator. All right, that about does it for waves and the Doppler effect. So we are pretty much almost done with this unit. Just a little bit more to go, and we'll have one left to go. All right, take care.